Okay, folks, welcome to lecture 15. And in this lecture, we're going to take a look at pharmaceutical calculations and moles. But now, I'm not trying to teach you chemistry in this lecture. What we're really doing is taking a look at the role of mathematics in these types of calculations. So just some general kind of tips in solving these problems. If there's lots of units in a problem, grams, milligrams, micrograms, it's usually good advice to bring all the units to the smallest unit. This just helps eliminate decimals mainly. Mainly though, you do need to have all your units at the same kind of prefix or whatever. It can be often helpful to convert big values to scientific notation. So say if you had 20 million capsules to be made, it might make more sense to write it like this. Or often, guys, is 20 by 10 to the power of 6. Sometimes it's more useful to write it like that, as we'll see later. Just it makes the division of this number, if we need to, a little bit easier. And then, guys, we're really just looking at, are we multiplying these values or are we dividing them? And the context of the problem then determines which is the most appropriate operation. Before we begin though, guys, we're just going to introduce the use of triangles for solving stuff out in maths. So say if we were looking at a journey, so say a distance of 100 kilometers, and the person was traveling at 50 kilometers per hour for a period of 2 hours. We can kind of represent this journey with a triangle. And if we don't know any element, any variable, we can always use the triangle to solve out the unknown. So, say if we wanted to work out the distance, we didn't know the distance. Well, the distance is speed by time. So it's 50 kilometers per hour multiplied by 2 hours. The hours will cancel. We multiply. So we'd be able to work out the distance was 100 kilometers. Or alternatively, say if we didn't know the time taken. Well, the time is distance over time. Distance over speed, my apologies. I should use V for speed really, but anyway, we'll just use the first letter. So time, guys, is distance divided by speed, so that's 100 kilometers divided by 50 kilometers per hour. So this will give us 2, and when we look at the units, guys, we have kilometers divided by a fraction, so we would flip and multiply and they would cancel out and we would get 2 hours as our answer. But we use the triangle mainly just to deal with the numerical component. Similarly, guys, if I need to work out what speed was the person traveling at, well, speed is distance over time. So in this case it's 100 kilometers over 2 hours. So that's the number bit. This is kilometers, the units, this is hours. So my number is 50 and my unit then is kilometers per hour, and that's the speed. So that's how the triangles work, guys. You kind of cover over whatever you're interested in, and the triangle will tell you then whether we're multiplying like this, speed by time, or whether we're dividing like in these two cases. Time is distance over speed, or speed is distance over time. So we're going to be using these triangles kind of throughout this lecture and a bit of the next lecture as well. So now we're going to take a look at the formulation of tablets and capsules and the like, where we've got a total amount of powder or something formulation and it's going to be made up into a number of capsules, pills, tablets, loads of different types of ways of drug delivery. So here we have a similar setup. Distance is speed by time. So we can set this up using a triangle. Here's the triangle. Total is on the top. So whatever sits on its own, guys, sits on the top of the triangle. So now total is the number by the dosage. Number is the total divided by the dosage. And then the dosage of the tablet is the total amount of drug divided by the number of tablets we're making. And usually, guys, trying to figure out from the question which bits you're given is often the biggest challenge. Once we establish what bits we're given and what we're looking for, then really we're trying to ask ourselves, well, are we dividing or are we multiplying the values we know? So we'll take a look. But before we do, guys, this is something that students always struggle with, so I tried to put together a little slide to help you. So the total amount, if we're looking for the total amount, usually the question will have the words how much amphetamine is needed to make blah blah blah. Generally, any mass greater than 1 gram in the question, you can be pretty sure that that's going to be the total. So if you're told 200 grams is you can be pretty sure that 200 grams is going to be the total for any of your calculations. Then, guys, the number, usually how many tablets can be made from 20 kilos of amphetamine divided into 2 microgram doses. If the number is given in a question, usually it'll be a big value, either in words or numbers, and there'll be no units, there'll be no milligrams, micrograms, grams, kilos associated with it. So that's how you know you're dealing with the number component. There's no units, and if we're looking for the number, usually the question will have how many. And now the dosage, how much is in each capsule, tablet, and then we might often require your dosage to be in milligrams or micrograms. So anytime you see milligrams or micrograms, guys, that's the dosage. And in general, any value given less than 1 gram, you can nearly always assume that that's the dosage. So that's just to help you try and kind of figure your way through the problems, as in which values am I given and which value is being looked for in the question. And then you can use the triangle to determine, well, am I multiplying or am I dividing? So dosage, like I said, any value less than 1 gram is the dosage. Any value greater than 1 gram is generally the total. So that's a fairly good rule of thumb. So, how many 5 milligram tablets of amoxicillin can be made from 1.4 kilograms of pure amoxicillin formulation? So now, guys, first of all, we'll just take a look. Here's 5 milligrams. That's pretty sure that's the dosage. Here's 1.4 kilograms. That's the total. And because of the words how many, we're looking for the number. That's how you have to go through the question. You have to decide what values am I given and what am I looking for. So we're looking for the number. Number is total over dosage. So in this case, the number, the total, I'm going to bring everything to scientific notation. So 1.4 kilos, guys, is 1.4 by 10 to the power of 3 grams. The dose is 5 milligrams. Milli, 10 to the minus 3 grams. So my grams will cancel out anyway, which will leave me just with a unit. Now, guys, we have to do numbers do what numbers do. 1.4 divided by 5. 5 won't go in. 5 will go into 14 twice. Bring another 0. And we get 0.28. So numbers do what numbers do, guys. I get 0.28. Now powers do what powers do. I'm subtracting, guys, the lower power from the upper power. It's essential not to make a mistake there. We have a minus, essentially multiply, we have a double negative. That becomes a plus, so this is by 10 to the power of 6. Finally now, guys, we need to write this as a whole number. It'll be 2.8 by 10 to the power of 5. That's into scientific notation. And finally, 28. I need to make sure the decimal point is 5 places away from, so we're there. Yeah, 2.8 is 280,000. So that's how many tablets of 5 milligram dosage can be made from 1.4 kilos. And you don't need the comma if I just helps resolve the answer a bit more clearly. 3.6 kilos of codeine is to be made into 90 million tablets. So the numbers, guys, are kind of nearly unwieldy, but determine the dosage. So it's telling us what we want. We want the dosage. Dosage, put our finger over dosage. Dosage is total over number. So the total, guys, I have 3.6 kilograms of codeine. Kilo, 10 to the power of 3. And it's to be divided by the number. Now the number, guys, is going to be 9 by 10 to the power of 8. I hope you're okay with that. Now numbers do what numbers do. 3.6 divided by 9. That will give me 0.4. And here, guys, I have... Oh, sorry, that's not 10 to the power of 8. That's 10 to the power of 7. Excuse my mistake. I'm sure you're all screaming at the video. Yeah, 10 to the power of 7. Phew. So here, guys, we get numbers do what numbers do, and then powers. And it's always a good idea, guys, just to write out what's going on. This will be 10 to the power of minus 4. Now, first thing I'm going to do is just bring it to scientific notation, because at least I'm on safer ground. This side has got bigger, so the other side gets smaller. We subtract on the power, remember. Decimal point moves to the left, increase the power. Decimal point moves to the right, which is what it's doing in this case. We decrease the power. And the best way to do that, guys, is simply add minus 1 to your power. That way you'll never go wrong. And finally now, guys, we need to go to micrograms. So you have to be very careful treading your way through these. We're going down again. We're going down to micro, 10 to the minus 6. So same idea. This side has got smaller because we added 1. So this side gets bigger. So finally then, guys, our answer, what's the dosage in micrograms? It's 40 micrograms. And now again, guys, I know I'm kind of moving through these fairly quickly. I'm not suggesting they're easy. What I'm really trying to do is get you guys practicing in and out of these powers. That's really what I'm trying to do, because it's such an important skill. How many grams of the antibiotic tetracycline are needed to make 50,000 40 microgram capsules? So there's a lot of words going on with numbers, and I do write them to kind of challenge you. So here, guys, well, here's a dosage. That's less than 1 gram. That's my dosage. Here I've got a big number. There's no units attached to it. Sorry. So that's my number, and it makes sense. There's 50,000 of these tablets. And how many, guys? Remember, that's usually asking you to find the total. And that's your most important, guys, step in the start of the question, is figure what do I have and what's needed. So we're looking for the total. Total is the number by the dosage. So in this case, guys, we have 50,000. I'm going to write it out first, just to, by 40 micrograms. So I'm going to go to scientific notation. 5 by 10 to the power of 4. And that's multiplied by 40 by 10 to the minus 6. That's the micro. My answer is still going to be in grams, guys. The grams unit with weight. Now, guys, numbers do what numbers do. 5 by 40 is 200. And powers do what powers do. We add the powers. So we have 200 by 10 to the minus 2 grams. Now we need to make this side smaller. Decimal point moves 2 places to the left. Remember from the clown, decimal point, the diagram. If the decimal point moves to the left, we increase the power 2 places. So we'll end up with 10 to the power of 0 grams. This side, the left-hand side, guys, has got smaller by a factor of 100, so the right-hand side of our number must get bigger. So finally then, how many grams is needed? In total, guys, there's just 2 grams. That's our answer there. Take a look at one more. Now in this case, guys, we start off with pounds of amphetamine. 33 pounds of amphetamine is to be made into 5 million tablets. How many milligram of amphetamine in each tablet? So we're looking for dosage. But first of all, guys, we're going to have to bring our pounds into kilograms. We're going from pounds into kilograms. We use the reciprocal. 33 divided by 2. Sorry, I better just write this out properly. 33, 1 pound, sorry, I'll be more formal. 1 pound is 1 over 2.2 kilos from our conversion on the left. So now we multiply both sides by 33. On the right hand side, guys, multiply the top by 10 and the bottom by 10. And then, guys, we'll see, well, 11 will go in here twice and 11 will go in here 3 times. So we've got 30 divided by 2. So our first step, guys, is to work out, well, how many kilos do we have? This is from the lectures from last week. And we see we've 15 kilos. So that's our total. 15 kilos of amphetamine. Now the problem runs very similar to the previous ones. We need to get our triangle. We have our total, 15 kilograms. We have our number. And we're looking for the dosage. Dosage is total over number. The total is 15 kilograms. So that's 15 by 10 to the power of 3. And the number, guys, 5 by 10 to the power of 6. Numbers do what numbers do. 15 divided by 5 will give us 3. And be careful, guys, 10 to the power of 3 minus 6 gives us 3 by 10 to the minus 3. And that is already, we don't have to adjust it, that is already in milligrams. So each tablet, guys, will have a dosage of 3 milligrams. So even though it's dressed up, guys, as a very scientific problem, you can really see the real thing that's going on is converting into scientific notation and then multiplying or dividing as appropriate, as defined by the triangle. So don't stray too far from the basic maths. Like, that's really what we're looking at. Numbers do what numbers do, powers do what powers do. So now, a couple of questions to give a wee go. There's the triangle. So just have a wee go at them. Don't, guys, be put off by the words. I just googled lots of scientific sounding formulations. Amoxicillin, amphetamine, codeine, tetracycline. Really, what's the dosage? What's the total? What's the number? What am I given? What am I looking for? So we'll push on again, guys. We'll just need that for the last problem. It's similar to the one we just did. Now, guys, we're going to take a look at moles. Again, I'm not trying to teach you chemistry. I'm really just going to show you how a triangle, just like the one we looked at, can apply to moles as well. So this isn't too bad. So a mole, guys, is essentially, without getting into the details of it, mole is the amount of stuff. It's nearly always a mass. How many grams? How many kilograms? The mole of a substance depends on the nature, the chemical formulation of the compound. What's its molecular weight? So I'm not going to go into molecular weights or anything like that, guys. That's for your chemistry lectures. I will always give you the molecular weights of any compounds we need. But here, guys, again, we have remember, our distance is speed by time. This formula is written in the same format, so we can do a triangle again. And again, grams is going to be on the top. Whatever sits on its own is on the top. Now, if we want to find grams, cover over grams. Grams is moles by molecular weight. Moles, grams divided by molecular weight. And now I'd never really ask you the molecular weight, but if we needed to, it would be the grams divided by the moles. But generally, guys, I won't ask you that one because usually we know the molecular weights of what we're dealing with. So how many grams are there in 1.5 moles of calcium carbonate? I love calcium carbonate, guys. We're looking for moles. How many grams is there? But calcium carbonate, guys, has a nice, easy molecular weight. It's got a molecular weight of 100. I'm not going to get too into it. 40. 3 oxygens is 48. Plus calcium is 100. So 40 plus 48, 88, plus 12 is 100. So I use calcium carbonate quite a lot. I try and make sure all the compounds I use, guys, have nice, easy values to work with. In general, not always. So now we have the molecular weight, guys. We're told the number of moles. So it's fairly straightforward now. Grams is moles, 1.5, by molecular weight, by 100. So our answer then is 150 grams. Another one. How many moles are there in 27 grams of HCl? Here's our molecular weights. Hydrogen is 1, chlorine is 35. So our molecular weight, guys, is 36. How many moles? Well, moles, grams divided by molecular weight. So in this case, guys, moles. Note we don't write an S, guys, just mole. Mole is 27 over 36. 9 will go in top and bottom. So there's 0.75 moles in 27 grams of HCl. So I could do loads of them, guys, but I think you get the general idea. Have a go with these ones now. Here's the molecular weights. Make sure you use these ones, guys, for any calculations on Moodle or for the CA tests. How many moles is there in 25 grams calcium carbonate? So I'll always give you the formula as well, guys, and it's really just a case then of working out your molecular weights individually. So I'll let you guys have a go at that. And that, guys, kind of finishes us up for lecture 15. In the next lecture, we'll take a look at molarity and dilutions. And again, it's really just a case of applying the maths we've already looked at in a scientific context. So thanks again for listening, guys. Appreciate it. And we shall chat again in lecture 16.